Welcome to Analytics Mastery Academy. My name is Kunal. Welcome to this series. In this video, we are covering section 6, Troubleshooting, Monitoring and Optimization. It is also worth about 10% of the exam. We will look at Lakeflow Jobs monitoring, reading the Spark UI, common performance bottlenecks, liquid clustering, and cluster failure diagnosis. Let's start with monitoring at the job level. Every job run is logged with a start time, duration, status, and what actually triggered it. You can compare runs side by side to spot performance regressions. You can also drill into task level monitoring for each task run. You will see duration, output, error messages, and cluster details. The DAG view gives you a real-time visual of task status. Green means success, red means failed, and gray means skipped or not yet started. This makes it easy to spot upstream blockers immediately. For alerting, you can set email or a webhook alerts on job start, success, failure, or when a run breaches a duration threshold. And connect those webhooks to something like a PagerDuty or a Slack. Two things worth tracking over time are pipeline runtimes, since a sudden increase usually signals a data volume increase or performance regression. And the second thing is failure rates. A failure rate above roughly 5% points to a fragile pipeline that needs robustness work. For the exam, picture this scenario. A job that used to take 30 minutes now takes 90. Where do you look first? The run history view to compare timelines. Then you drill into slow task. Then you go into the Spark UI for the task stage metrics. That brings us to the Spark UI itself. The stage view shows you minimum, median, and max task duration for each task. The large gap between the median and the max is your first signal of a data skew. Shuffle read size tells the same story in a different way. If one task has 5 GB shuffle read while the other sits around 400 megabytes, that's a heavily skewed partition. Data skew happens when one or few tasks process disproportionately more data than the rest, usually caused by skewed join keys or partition keys. Disk spilling happens when a task doesn't have enough memory and start writing to the disk instead. You will see this as a spill memory or spill disk columns in the stage metrics. Shuffling overhead shows up as a large shuffle read and write bytes in a stage, a sign of an expensive join or a group by. Consider broadcasting a smaller table or partitioning differently in this case. And task deserialization time. If this is high, it can point to large broadcast variables or complex UDFs, worth rethinking about your complete approach. This data skew pattern is straight out of the exam guide, and it's exactly what a sample question 1 tests. Most tasks finish under 30 seconds, but one task takes 10 plus minutes. Shuffle read, median 400 megabytes, maximum 5 gigabytes. It's a 12x skew ratio. The fix is adaptive query execution with skewJoin handling, which splits the oversized partition automatically. Let's map symptoms to the fixes because that's exactly how the exam tests this particular section. Data skew. Symptom is one straggler task. Fix is enable AQE with spark.sql.adaptive.enabled equal to true with skewJoin handling or salt the skewed key. Excessive shuffling. Symptom is large shuffle read and write. Fix is broadcast small tables, increase shuffle.partitions or repartition before the join. Disk spilling. Symptom is non-zero spill columns and the fix is increase executor memory, reduce shuffle.partitions so you get fewer for the but larger tasks or filter earlier in the pipeline. Too many small files. Symptom is slow reads, and a lot of small tasks. Fix is run optimization for compaction combined with ZORDER on your query predicates and enable auto optimize. Small partition count. Symptom is insufficient parallelism and slow stages. And the fix is increase shuffle dot partitions or call repartition before any heavy operations. Out of memory errors. The symptom is an out of memory error on the driver or the executor. And the fix is increase the relevant memory config, avoid calling collect on large datasets, and check for memory leaks inside the UDFs. The exam will typically describe a symptom and ask you to identify both the problem and the fix. So knowing this table will help you directly. Now, liquid clustering and predictive optimization. Two newer features that reduce manual tuning work. Liquid clustering replaces Z order and static partitioning with a flexible auto-optimized clustering strategy. It co-locates high cardinality columns so queries stay fast. You enable it with a create table T cluster by some columns. From there, Databricks automatically manages clustering as data changes. No manual optimize is required. The benefit over Z order is that liquid clustering is incremental. Only newly written data gets clustered. So there is no full table rewrite as such. That makes it much better for frequently updated tables. Predictive optimization works alongside this. Databricks automatically runs optimize, vacuum, and analyze based on how a table is actually used, so no manual scheduling is required. Enable it at the Unity catalog level to cut down the DBA overhead, especially on large, frequently queried gold tables. For the exam, note this distinction. Liquid clustering is incremental and self-managing. Z order is a one-time reorganization. Static partitioning is rigid and can actually cause skew on low cardinality columns. Know when each one is the right to use. Now let's cover cluster level troubleshooting. Cluster startup failures commonly come from an invalid init script or a library installation failure, a cloud quota being exceeded, or some permission issues on the cloud storage. To diagnose a startup failure, check the cluster event log in the clusters UI. Init script failures show up there with error details. Library conflicts happen when two libraries need conflicting versions of the same dependency. The symptom is usually import error or no class definition found error at the runtime. The fix is to pin library versions in your requirements.txt or use cluster scope libraries installed once, consistent for every job that runs on that particular cluster. For the out of memory error on the driver, usually caused by calling collect on a large data frame, large broadcast variables, or accumulating results in the driver memory. Fix this by using distributed writes or increasing the driver memory. For out of memory error on an executor, usually caused by large shuffle partitions, complex joins, or UDFs with high memory usage. Fix this by increasing the executor memory or reducing shuffle dot partitions. So here is the practical takeaway. Use cluster scoped pinned libraries rather than ad hoc notebook installs. And always distinguish driver out of memory, check collect first from executor out of memory, where you check skew shuffle size first. So recapping section 6 here, the run history view lets you compare durations over time to catch regressions. In Spark UI stage metrics, a straggler task combined with a large supple read means data skew. Adaptive query execution automatically handles skew joins. Liquid clustering replaces J order. It's incremental and self-managing, and it's better for tables that update frequently. For out of memory diagnosis, driver out of memory, check collect. Executor out of memory, check for skew and shuffle size. In the next video, we will cover governance and security. Thanks for your time. Have a nice day.